Okay, we are in work energy principle, and I need to oil my chair. So this is what I call the Iron Man problem. So if you saw Iron Man, and if you didn't, you should, because it's really important in the Marvel universe, the Marvel Cinematic Universe. Sorry. And so at the beginning, spoiler alert, spoiler, I misspelled that, alert. But if it's like over 10 years old, then it's not a spoiler. I don't think. That's just me. Okay, so here's Iron Man. He built his suit and he's flying away and then he crashes in the desert. So he falls from some height H and he impacts in the sand and makes a crater. And the crater depth is S. And so the question, he has mass M. And so the question is, what kind of force what kind of average force is exerted on him during the impact? And what's the average acceleration during impact? And so we can pick some values for H and M and all this stuff, and I'll write that. Let's say mass. Let's say he's got the suit on. So let's say 200 kilograms is kind of high, but yeah, it's iron, right? 200 kilograms. H is going to be, let's say, 15 meters, and then S is, I'm just kind of eyeballing it here. Let's be generous and say 1.8 meters, and then the magnitude of the gravitational field is 9.8 newtons per kilogram. Okay, so that's my estimates. You can make your own estimates, and in fact, I'll link to my calculations at the end so you can change it to your own thing. So we are going to use the work energy principle. Why? Sometimes I can't spell things. Okay, so because I don't, if I care about time, then I don't want to use the work energy principle. But in this case, I don't care about time. It starts here, it ends there. And in fact, we could even call 3 positions. 1 is right here at the beginning, 2 is right when he contacts the sand, and then 3 is once he stops. So you could have 3 different positions. And we're talking about positions and velocity. Then that right there says, hey, use the work energy principle. Now, as soon as you do that, the next thing you should say is this. What's my system? Because this matters how you set things up. What do you pick as your system? Now, if I pick just Iron Man as my system, then I need to consider what forces do work on him. Well, while he's falling, there's a gravitational force pulling down. But then while he's impacting with the sand, there's a normal force or some other force acting on him. Okay, let's call it, I don't want to call it normal. It is a normal force, but I'm going to call it F sand. I like that better. So I'd have 2 forces doing work on him. But I think in this case, it's probably easier to say the system is Iron Man plus the Earth. In that case, there is no external gravitational force on them because that's part of the system. So that means that I'm not going to have work done by gravity. I'm instead going to have a gravitational potential energy. So this is going to be my work energy equation. The work is the change in kinetic plus change in gravitational potential. Now, the next thing I need to do is pick my points. And in this case, I'm going to go from 1 to 3. I'm not even going to use 0.2. I think a lot of people would say, hey, let's find out how fast he's going right before he hits the ground. But you know what? That doesn't matter. Okay? It just doesn't matter. So I'm going to go 1 to 3, and then we'll talk about this 0.2 afterwards. So in that case, during 1 to 3, what forces do work on Iron Man? Well, while he's impacting, I have this. I have that. And this one doesn't do work. It's an internal force. So I just have that. Okay. So I have the force of the sand will exert on him and it will do work. But how much? So I could say work is, and I'm going to write this out as a scalar, force of the sand times how far that object moves, which in this case is going to be S, times cosine of 180. Because as he's moving down, the force is pushing up. The angle between those two is 180 degrees, so it's cosine of 180. Notice that the sand doesn't do work on him the whole way he's falling, just during this last part. And this is assuming that that's a constant force, but it's not, so we're really calculating the average. So that's the work done by gravity. So I mean the sand, I can actually write that as negative Fs, S, that's the sand, and that's the distance S. So now I can write the rest of my stuff. This is going to be the change in kinetic energy, K2 minus K1, plus U2 minus U1, not the band. Okay, that was a bad joke. I take it back. Okay, so I'm trying to find that force. I know a value for S. What about the kinetic energies? Well, here's the trick. What's his kinetic energy when he starts from rest up here? 0. What's his kinetic energy at point 3? 0. Okay, so now I just need this change in potential. So let's write this as negative Fs equals mgy2. Let's just call this down here y equals 0. So this is going to be mgy2 is 0 minus mg, what's the y up here? It's going to be h plus s. And so I want to solve, oh, there's an s right there. So I want to solve for f. So the negatives cancel, and I get Fs equals mg h plus s over s. That's it. So I know all these values, and I can calculate the force. But also, look, I can do this one on one page. I can also calculate the acceleration. F net, okay. F net equals MA. This one is a little bit tougher because, let's do it anyway. Okay, in the y direction, this is one dimensional. So this is going to be Fs minus mg equals ma. So a is going to be equal to Fs minus mg all over m. So I'm going to calculate Fs, I'm going to plug it in here, and then I'm going to find the acceleration. And the acceleration is important because of reasons. Okay, I am writing this up. M equals 200, G equals 9.8, H equals 15, S equals 1.8, and so Fs equals M times G times H plus S divided by S. And then A equals Fs minus M times G divided by M. And I get Fs is, ooh, it's high, 1.8 times 10 to the 4th newtons. And for A, I get 81.7. So meters per second squared. And then the one thing that's also nice is to get the acceleration in G's. 8.3 G's. Okay, that's actually encouraging because the way that we normally determine if a human gets damaged or not, or severely injured, is based on the acceleration. And so an acceleration of 8.3 Gs is super survivable. There's this great NASA graph that shows maximum G force tolerance as a function of time. So for some short time intervals, you can withstand a higher G force acceleration. And for longer time intervals, that's lower and lower. But 8.3 for a seriously short amount of time is indeed doable. Okay, there you go. The Iron Man problem. We'll do some more work energy problems later.